Hello everybody, we are going to talk about optical rotations in stereochemistry. What's optical rotation? Is it like when you go to the optometrist and they're like turning things around? Well, not really, but here we're going to take a chiral molecule, something that has got either R or S stereochemistry, and those are the only two possibilities. And you're going to put it in a tube, send some light to it, see the deflection, and then we can actually calculate how much of it is in there, and sometimes even use that number to identify it. All right. So here we go, optical rotation. So what do we do in an optical rotation? First of all, we need a light source. We need to take a light and shine a light in our solution. So let's say we have a light like this. If it is chiral, then it's going to turn it, rotate it, either to the left or the right. And the light knows whether it's R or S, something that we would never be able to figure out. But the photons here are smart enough, intelligent enough to know whether it's R or S. Now, we call it dextrorotatory, levorotatory, because R sometimes can go clockwise or counterclockwise. S sometimes can go clockwise or counterclockwise, but it's always going to be the opposite for a pair of enantiomers. So R goes levorotatory, then S will go dextrorotatory. All right, let's look at that. Optical rotation. So we have a light source, which is just basically like a sodium bulb typically, and we got to put that light through, first of all we got to put it through a monochromator, so we only get one wavelength, and the wavelength that's typically standardized is the sodium 589 nanometer lambda. That's called the D line of sodium. So we call that whatever that rotation in alpha D. And so after the light goes through here, so you'll have the same lambda light coming through, and then it's going to go through what you call a polarizer. So the polarizer will only allow light in a certain direction to come over. So the light would either come over in Z direction, or it'll come over in the X direction, or it'll come over in the Y direction. It's usually light comes in all directions, but we are only going to allow light, let's say, that comes in one direction and filter out all the others. So that's a polarizer. Let's say it's got grids like this, kind of a very precise instrument. I'm just drawing a grid here, you know, like in your car, but it's nothing like that. Okay, so it's like a very prismatic structure that will only allow light in one direction. So the light comes through and it goes in one direction, and now it's going to hit the sample. So you'll take a glass tube, very beautiful clear glass tube, and this is about 10 centimeters long, and 10 centimeters is called a decimeter, believe it or not, and that is the path length. We call that the path length. The light is going to go through there. Now you're going to take that light and you're going to put some chiral molecules in there. So you got to have a chiral molecule. If you don't have a chiral molecule, you're not going to get the rotations that you would see. If it's an achiral molecule, there won't be any rotation. I'm just going to draw something here. This is a chiral molecule. It can be a mixture, it could be pure, it doesn't matter as long as there's chiral. Okay. And the only time the chiral molecule is not going to show you deflection is if you have RNS 50/50 raceme or achiral. Those are the only two optically inactive compounds. All the others would be optically active. Okay. So the light goes through here, and then the molecules are going to turn that light. If it is only one enantiomer, it's going to turn it in one direction. And so then you're going to have an eyepiece here, and you're going to watch that, and it's going to come out, and then you will see if it comes out at an angle, you'd have to turn this observing piece here to the angle in which it's going to come out. So this is going to now rotate like this. And then you would get a view of that, and it's going to come out, let's say, like this, you see, like that. Then you would have rotated it by an angle of alpha. Now you can use that angle, and then you can use that to calculate a standardized alpha. So now alpha depends on many things. So the angle of rotation, or alpha, depends on the concentration. More stuff, you might have more angle. It depends on how my concentration is. Grams per milliliter concentration. It depends on how long this path length is. So we keep it standardized at 1 decimeter path length. It depends on the temperature. We keep it standardized at 25 degrees centigrade. Celsius temperature, and it would also depend on the alpha, okay, and we keep that standard at 589 wavelength. So when you keep everything standardized, it's called alpha D. Standardized optical rotation is alpha D. D for the D line of sodium. So alpha D is going to be alpha that's observed, we can call that alpha observed, over concentration times the path length. These are all standardized. So here, again, I'm going to say concentration is going to be in grams per milliliter, and length, path length, is going to be 1 decimeter. Temperature, we fix at 25. Sometimes I've seen 20, but it's mainly 25 degrees centigrade or Celsius. And lambda is 589. When you have all of these conditions fulfilled, we'll call this alpha D. And the way to convert alpha to alpha D is, well, assuming temperature is this and lambda is this, it's going to be just dividing by the concentration times the path length, which is also always 1. So it's basically this over grams per milliliter of your sample. Let's work a small problem just to show you what it means. So let's look at some examples here. Okay, enantiomeric excess, something that you would do when you're probably doing some research or doing something on your own with chiral compounds. But alpha D is something you might probably do in your lab. So here, when you have your wavelength come out and hit this grid and you rotate it, so you can see it, you see like a half moon, and then you see a line where you can see that it's coming, it's really very distinct, then you will know that you've rotated it. The only thing we know about this, that if you rotate to the right, that's called dextrorotatory. When you rotate to the left, that's called levorotatory. So you'll have either a D or an L or a DL mixture, but not a 1-to-1. Now D can be R or S, L can be R or S. So the direction here has nothing to do with our direction going clockwise and counterclockwise with the 1, 2, 3, 4. That's something we've kind of set in our heads. But nature has its own way of determining which goes counterclockwise and which goes clockwise. And that's entirely up to the structure of the molecule. And that's something we can't fathom. We don't have an idea of how the photons decide to go right or left. But what we know is for one of the enantiomers, if it goes in one, let's say clockwise, 55 degrees, then for the other enantiomer, it'll go counterclockwise, minus 55 degrees. It'll be opposite and exact same angle of rotation for enantiomers. All right. So let's say we put in 0.5 grams in 25 mLs, and that kind of goes in this tube. Some of it goes in this tube, but the concentration is 0.5 over 25 milliliters. What's the alpha D? So we have to standardize these values. So we'll just apply the equation. In this case, it's really straightforward. Alpha D is going to be alpha observed, and this is what they say has an observed alpha of negative 0.850 degrees in over concentration, which is again gram per milliliter. So it's already given to you in gram per milliliter. So that's 25.0 ml. You don't have to convert this to moles and so on. And L is always going to be a decimeter. The polarimeter has a fixed length. So that is going to, then all of these units would give you an alpha here when you put the numbers in of minus 42.5 degrees. Now, if you have a mixture of this D and L, so if of one of them, it's going to give you that. If you have a mixture of this, and the alpha D is minus 8.21, how much of the L enantiomer is present in excess? Well, how do I know it's L? Because the sign is negative. If the sign is negative, it's going counterclockwise, which means it's levorotatory, negative. If the sign is positive, then it's going to the right. That means it's dextrorotatory. So then over here, it's getting minus 8.21. So how much in excess is present? So obviously, this is not a pure solution. They already tell you there's two enantiomers mixed in there. And one of the enantiomers is in excess, which is why it's negative. So the L is in excess. How much in excess is it? So let's say you have over here enantiomeric excess. Let's say you have a solution, and if you have 100% of one, it'll be either D or L. But let's say you have an excess of 20% of D or L. 20% excess, let's say in this case, just like excess of D or L. That means that's your enantiomeric excess. That means the rest of the 80%, so let's say the yellow is going to be your D, let's say. That means the rest of the 80% is going to be a mixture that is equal of D and L, which is why it's not showing any kind of optical activity. Because if, let's say, this is going clockwise, then the green is going counterclockwise, then it's going to be equal and opposite. So for racemic mixtures have zero optical rotation. An excess of one of the enantiomers, we don't know which one, could be D or L, then you would only see optical rotation due to the excess. Let's say this is going to be L. Then you will have L, all of that, 20% would be pure. Another 80% would be a mixture of the D and L. And if it's a raceme, and it would be a raceme because it's optically inactive, it would be a 1-to-1. So example, this is going to be D and L. This is L and this is D. And D to L would be a 1 to 1. So then alpha is going to be cancelled out. 0 optical rotation. So this is what you're going to see. So 20%, let's say example L, 20% is, let's say, L. That means you have L here and you also have L here. How much do you have? 50% of the remainder. So 100 minus 20% is going to be DL mix. And since it's a raceme, we know that it's going to be 100 minus 20% divided by 2 is going to be L, and you would have the exact same amount of D percentage. So we can say the amount of excess, enantiomer excess is 20%. But in the entire solution, you would have a 80 over 2, 40% D and 60% L. So in this case, you would have 40% is your D, which is the dots here, and this is going to be obviously 40%. So 20 plus 40% is going to be the green L. And just 40% will be the D. So therefore 60% L, 40% D. This would make it have a 20% excess of one of the enantiomers. That's what we call enantiomeric excess. So let me go over this one more time. So we have a solution, a solution in here, let's say. It's got D and L isomers, 2 enantiomers. They are not in equal amounts. They're unequal. One of them is more than the other. We want to find out how much more is one of the enantiomers compared to the other. That means what is the excess of that enantiomer? That's called enantiomeric excess. So we can find out that amount from the alpha. So when you put this in mixture through the tube, this racemic part where they're equal, D and L will cancel each other out and will be optically inactive. So you won't see this. You would only see this. And so you'll get an alpha for that enantiomeric excess. But we would know from the solution how much excess that is, because you can compare that to your pure sample. So you compare the mixture to the sample, you would know what percentage of one of the enantiomers is there. Okay? Then when you subtract that from 100, then that would be the amount of the raceme. The raceme has a 50-50 of the D and the L, which is why they cancel out. So if you divide the amount of raceme, percentage of raceme by 2, that would give you the amount of each of the isomers, percentage D and percentage L in the raceme. All right. So here's a problem that asks you that. So the alpha D is 8.21. How much of the L enantiomer is present in excess? So enantiomeric excess is going to be the amount in the mixture, alpha of the mixture over alpha of the pure times 100%. That will give you the percentage of this. Then you can find out how much the other one is. So let's say that is going to be a certain percentage, EE percentage, let's say. Then 100 minus EE percentage over 2 is going to give you percentage of other enantiomer. So here alpha percentage EE is going to be 8.21 divided by, here is the standard, which is minus 42.5 times 100. So this is a lower concentration. This is if it is pure. and that is going to be 19.3%. So 19.3% is what is in excess. This is what's in excess. So the rest of it, that's 100 minus 19.3, which is 80.7, is a DL raceme. Since this is negative, you would say this is L. This is DL 1-to-1 raceme. Therefore, half of that is going to be D and half of that is going to be L. So here is a DL mixture. So 50% of that is going to be D and 50% is going to be L. What is the percentage of D? D enantiomer, that is going to be 100 minus 19.3 divided by 2, and that is going to be 40.35. Now you'll have 40.35 L in here as well. So you can add these two and you will get total L is going to be what's in here plus the pure, 43.5 plus 19.3% total, and that is going to be 59.65. And it should work out that when you add these two, obviously you're going to get 100% because that's what's in the mixture. So I hope that's clear. If not, let me know. So here's another example. A sample of adrenaline has an alpha D of 47.7. Pure adrenaline has 53. How much is the impurities? So when you put it through a tube here, for a lot of the drugs out there, we can find out the enantiomeric excess. Or for sugars, or for proteins, or all the natural products that are chiral. If it's a mixture, you can put it through there, find out the rotation, find out the rotation of the pure, absolute rotation, and then we can find out the percentage, how much is the impurity. So this is a really quick way of finding out how pure your sample is. All right. So percentage enantiomeric excess, we can use this. You can see the sample is like a mixture because it's impure, minus 47.7. And the pure adrenaline here, they say, is 53.0. But it's a different sign. But that's okay. Ours is minus. This is for the pure. So we will take the pure as also the L. So the L would be the opposite of that. This is they're giving you for the D times 100. That's your enantiomeric excess, and that's going to be pretty high. That's about 90%. 90, well, in this case, you have 3 sig figs, 90%. Which means if you take the sample, 90% is only pure adrenaline, which is L. So this is going to be L. Is going to be 90%. The rest has got L and it's got D. And we know that's only 10%. And because it's optically inactive, it means D is equal to L. Is 1-to-1. That means it's a raceme. So then it's 10%. Half of it is D and half of it is L. So then it's going to be 100% minus the percentage enantiomeric excess. That's this divided by 2 is going to be percentage of other enantiomer. So that's going to be 100 minus a 90 over 2. That's going to be 5% of D. We know for sure it's D because this is negative, therefore it has to be L. If it's positive, then it is D. That's kind of how we assigned it. So 5% is the impurity. There's another one that doesn't give you any alpha. It's saying a mixture has 12.5 moles of, let's say, R2-bromobutane and 3.5 moles of S-bromobutane. What's enantiomeric excess? So which one is going to be in excess here? Obviously this is more than this, so this is going to have an enantiomeric excess. It is 12.5 moles. 3.5 moles of this would go in one direction, and 3.5 moles of this would be cancelled by that. So we'll have an excess that is 12.5 minus 3.5. So percentage enantiomeric excess when you have doing in moles is going to be R, let's say in this case it's R and this is S, R minus S, because that's the optically active part, over R plus S, that will be the total number of moles, and times 100. In this case it's going to be 9.0, and this is 16.0 times 100, and that's going to be 56.5%. If this is 56.5 in excess, what is the percentage in the solution? And we can find that out as well. So we can kind of test it out to see if this is true. Is this really true? Let's see. So here we have a solution, and it says 56.5% of that is going to be, in this case, R, excess of R, enantiomeric excess of R. So if that's 56.5, then the rest is going to be 100 minus 56.5, which is going to be 43.5. And we can see half of that is going to be R, and another half of that is going to be S. And S here would be the minor amount. And so if you divide this by 2, that would give you how much of S there is. Percentage S is going to be 43.5 divided by 2, which is going to be about 21.7. Right? Well, let's see if we get, that's what we get from here. So the S is going to be, percentage S here would be 3.5 moles over 16 moles when you add them up total, times 100. And that is going to be, if you put that on your calculator, that's about 21.8%, pretty darn close to this one, right? So therefore we can tell that yes, this is correct. We can arrive at it in multiple ways, all right? In summary, I just want to tell you that covered optical rotation, which is a very, very useful technique to find out the purity of things and the amount of one of the enantiomers in a mixture of enantiomers. So this is a really nice way of finding out enantiomeric excess. If you have any questions, don't hesitate to ask me. Talk to you soon, guys, and I'm sure there are lots of videos also online, so please watch those. They will show you the actual technique of how this is all happening, and I'm sure you'll benefit from looking at those. There are lots of other nice, lovely videos out there. Thank you. Talk to you soon.